First, a brief history of physics and astronomy.
The ancient Greeks believed that it was the Earth that was at the center of our universe. Their model had 7 visible orbs moving in circles around the geocentric Earth. These were the Moon, Mercury, Venus, the Sun, Mars, Jupiter, and Saturn. It was actually the ancient Greek astronomer Aristarchus who first put forth the heliocentric view of our planetary system way before Copernicus. Aristarchus knew that the Sun was at the center of our planetary system over 2,000 years ago. His wisdom was actually accepted for about 2 centuries and was even explained in detail by Seleucus from Mesopotamia about a century later. Then, the scientific world again abandoned heliocentricity and turned to a kind of astronomical dark age that lasted for over 16 centuries. Why was the wisdom of Aristarchus abandoned for centuries? Why did the scientific establishment mistakenly go back to thinking that the Earth was at the center of our universe? The scientific establishment, led by Ptolemy, actually held the scientific community to this geocentric error and would not let go. We really do not want this kind of thing to happen again. Just think, the scientific consensus was incorrect for centuries, even after being exposed to the wisdom of the truth. Finally, those centuries passed, and in the 1500s, Nicholas Copernicus revived Aristarchus' idea that the Sun was at the center of our planetary system. This time, the idea, though not accepted at first, took off. What had been forgotten had been revived. A way of looking at the universe that made much more sense was reinstated. Copernicus, Galileo, and others convinced the scientific establishment that the Sun was at the center of our planetary system. In the 1600s, Isaac Newton, standing on the shoulders of Kepler, wrote down his famous mathematical theory of gravity. He related his legendary falling apple to the moon. He showed that the apple falling and the moon orbiting were actually the same phenomenon. The apple and the moon were attracted to the Earth by gravity in exactly the same way. This was truly astonishing at the time. During the next few centuries, a scientific revolution proceeded, with progress made in electromagnetism, optics, astronomy, and many other fields of science. When we finally got to the 1900s, that's when the controversies began. Albert Einstein postulated that light was also a particle, and Louis de Broglie postulated that the particle is also a wave. A weird mixture of theoretical physics ensued that still cannot be unified into a single understanding of how things work on both the microscopic and macroscopic levels. That is the aim of this new film, to have a single theory explaining both the micro and the macroscopic worlds in a unifying way. Hello, I'm your host, Andrew Gray, and welcome to New Wisdom Unifies Physics. We're going to be sifting through all the important experiments of the last century. We're going to add some new wisdom, and voila, out will come a unified physics. I'm excited to have this opportunity to share this with you, so let's get started.
Okay, let's get right to it. The first key experiment that we're going to consider is the X-ray frequency limit experiment. This experiment is the basis for all new wisdom physics found in this film, and its explanation will be key to understanding all future episodes. So let's consider the X-ray frequency limit experiment. Isaac.
Yes, Andrew.
Put up the X-ray graphic, please.
The Xray graphic is now showing.
Okay, thanks, Isaac. In this graphic, we have an X-ray tube. Electrons are emitted from the cathode, go across, and are blasted into a tungsten anode. The electrons bounce around inside the tungsten anode like ricochet rabbits. Okay. Now, if the electrons are jerked around like this, then so are their electric force lines, causing X-ray waves to go down the electrons' electric force lines. You must understand how X-ray waves are generated by accelerations of electrons back and forth. Now, the best way to study this is, of course, with Maxwell's equations and mathematics. But we're going to show a simulation so at least you can be familiar with the concepts. Isaac, run the electron simulation, please.
Okay, Andrew.
Wow, that's bright. Okay, imagine that you are traveling alongside one of the electrons in the beam and you encounter the tungsten. You will see the electrons being accelerated back and forth because of collisions with the charges in the tungsten. These back and forth accelerations are the source of the X-ray waves. So, the frequency of the accelerations are generally associated with the frequency of the X-ray waves. So, for example, if you have fast accelerations, then these would generate fast X-ray waves. Or, if you had medium fast accelerations of the electrons, these would generate medium fast X-rays. Or you could have slower acceleration of electrons. These would generate slower X-rays. The point is, the different frequencies of electron accelerations generate different frequencies of X-ray waves. So we're interested in this, so we set up an X-ray spectrometer, like seen in the graphic, to measure the different frequencies of X-rays that are emitted from the tube. The result is called an X-ray frequency spectrum. Isaac, put up the X-ray frequency spectrum, please.
Okay, Andrew.
Okay, thanks, Isaac. Okay, let's assume that the electrons in our beam have 20,000 volts applied. Then we might see an X-ray frequency spectrum like seen in this graphic. Now notice there are many frequencies of X-rays represented, but there's a definite frequency limit at 5 quintillion hertz or 5 exahertz. Now this is curious because if you do a raw calculation of how fast you would expect the electrons to be bounced back and forth, you come up with a number higher than the 5 quintillion hertz. So in other words, if you calculate what the velocity of the electron is when it hits the tungsten and take into consideration the number of charges per unit volume and calculate the collision rate, you come up with a collision rate greater than the 5 quintillion hertz. But experimentally, we only see the 5 quintillion hertz and nothing faster. This is very curious, and requires explanation. Okay, so now let's assume that the electrons in our beam have 25,000 volts applied. Then we might see an X-ray spectrum that looks like this in the graphic. Notice that again we have lots of frequencies represented, but there's a 6 quintillion hertz frequency limit in this case. Now again, this is very curious because if you do the raw calculation, yes, it's a higher frequency limit, a higher voltage, but you would expect from doing the raw calculation that you would get a higher collision rate than the 6 quintillion hertz, and you would see frequencies higher than the 6 quintillion hertz. But experimentally, we just don't see it. Okay, so now let's assume that we have a beam of electrons that have 35,000 volts applied. Then we might see something like this spectrum in the graphic. Notice here we have some spikes in the curve due to resonances in the material, but we still have an 8.3 quintillion hertz frequency limit. Again, this is curious because if you do the raw calculation, you would expect a collision rate higher. Say you might calculate that we have a collision rate of 10 quintillion hertz collisions per second. However, we still experimentally see the 8.3 quintillion hertz. This is very curious. A good analogy would be, okay, so let's say I take a garden hose and spread it across the lawn. Got a garden hose across the lawn, and then I pick up the end and I move the garden hose up and down 3 times per second. But I can only make a 2 hertz wave go down the garden hose. Now, wouldn't you be surprised if you took a garden hose and you moved it up and down 3 times a second, but you could only make a 2 hertz wave go down the garden hose? Well, of course you would be surprised. That's the same surprise that we have when we calculate a 10 quintillion hertz collision rate, yet we only see 8.3 quintillion hertz X-ray waves coming out of the tungsten. This is very curious. So let me be clear. The X-ray frequency limit only depends on the kinetic energy of the electrons in the beam and nothing else. The higher the kinetic energy of the electrons, the higher the frequency limit of the X-rays emitted. So, for example, let's say we replace the tungsten in the anode with something that's denser, something that has more charges per cubic volume. Then we might expect that when the electrons go into this denser material, it would have a higher collision rate and send higher frequency X-rays out because of the higher collision rate. Well, we just don't see this experimentally. The X-ray frequency limit is independent of the frequency of the jerks of the electron, jerks back and forth the electrons back and forth in the material, and it's independent of the material of the anode. This is very curious and requires explanation. But before we get to this explanation, let's review what we have learned. 1. We have an X-ray tube. The electrons hit the tungsten, are accelerated back and forth, generating X-ray waves down the electron's electric force lines. 2. The X-ray waves have a frequency limit that only depends on the kinetic energy of the electrons and nothing else. The higher the kinetic energy of the electrons, the higher the frequency limit of the X-ray waves emitted. 3. The X-ray frequency limit does not depend on how fast the electrons are supposedly bounced around inside the anode and are independent of the anode material. This is all very curious and requires explanation. So now we will see the explanation. Again, let's get right to it. Here's the explanation for the X-ray frequency limit. Isaac, put up the X-ray frequency limit summary.
Okay, Andrew.
Okay, thanks, Isaac. Intermittent pulsating electrons cause the X-ray waves to have a Nyquist frequency limit. Let me emphasize this. The X-ray frequency limit is a Nyquist frequency limit. The X-ray frequency limit is a Nyquist frequency limit due to the wave nature of X-rays and the intermittent pulsating nature of electrons. Now hold on here. This is new, isn't it? Well, yes it is, and it's very exciting to be able to share this with you. Now, if you're an audio engineer or a geophysicist, there's a good chance that you already know what a Nyquist frequency limit is. However, many of you may not be familiar with Harry Nyquist and his limits. So first, we must explain Nyquist frequency limits for these viewers, and then we'll use this concept to explain how intermittent electrons have a Nyquist frequency limit while emitting X-ray waves. Okay, the Nyquist limit. The best way to understand Nyquist frequency limits is by example from what we can actually hear. The Nyquist frequency limit is commonly found in audio engineering and will be a good analogy to apply to our X-ray waves. So we'll start with an audio Nyquist example. Isaac, put up our Nyquist audio system, please.
Okay, Andrew.
Okay. In this example scenario, we have an audio player and a speaker. And in between, we have put a special gate to illustrate the Nyquist limit. We shall call this gate the allow change gate. This gate keeps the voltage constant to the speaker except when an allow change pulse is applied every 1 millisecond, or, in other words, at 1,000 hertz rate. So in a sense, the gate is chopping the audio, making it intermittent at 1,000 hertz. So what would happen to audio going through this gate? That's the question that we want to answer. So let's start with a 100 hertz sine wave going through the gate to see what happens. Isaac, put up the 100 hertz test wave, please.
Okay, Andrew.
Okay, here we have a 100 hertz sine wave input. We would play this from the player on the left. To see what would come through the gate, we temporarily draw vertical yellow lines depicting when the voltage can change, and then only allow the voltage to change inside the yellow lines. We would get something like this. Here we see a 100 hertz wave shown in green that has steps in it. This type of output is typical in digital audio and is used most of the time. Notice that the wave coming out of the gate represents a 100 hertz sine wave fairly well. Okay, so let's continue. Next, let's do a 200 hertz sine wave the same way. Again, we draw the helpful yellow lines depicting when the voltage can change, and out of the gate comes something like this. Here we see a 200 hertz wave shown in green that has steps in it. Notice that this step wave represents a 200 hertz sine wave, but not quite as well. I think you get the idea. We want to increase the frequency of the input wave and see what happens. It will be better for us to use actual audio equipment to generate these waves so we can see and hear what happens. Isaac, roll the oscilloscope footage, please.
Now rolling.
Okay. Again, we start with 100 hertz. This time we can actually hear it and see it on an oscilloscope. And now, like before, let's increase the frequency to 200 hertz. Here's 200 hertz. And here's 300 hertz. And here's 400 hertz. We can already hear that the reproduction of the 400 hertz sine wave is starting to be a little problematic. That's a clue that we're approaching the limit. So here's 500 hertz. Let's stop here for a moment. The oscilloscope now shows a 500 hertz wave. Notice that the wave that's generated after the gate is a square wave. The 500 hertz green square wave actually goes up and down as fast as it possibly can, with 1,000 hertz pulses limiting it. Imagine an input wave that's faster than this 500 hertz. It would be very hard to represent a wave faster than 500 hertz by this method. Okay, well, let's see it. Let's go to 600 hertz input and see what happens. Here's 600 hertz. Notice that the frequency of the tone went down and not up. This wave generated from 600 hertz through the gate actually sounds more like the 400 hertz generated wave. This is called aliasing. See how some of the peaks of the 600 hertz wave are missed? Let's go back and forth from the 400 hertz to the 600 hertz generated waves. We're now at 600 hertz. Here's 400 hertz. And back to 600 hertz. And 400 hertz. Do you hear that the wave generated by 400 hertz and the one by 600 hertz sound very similar? This is typical near the Nyquist limit, which is 500 hertz. So let's go back to 500 hertz. Here's 500 hertz. And now to 600 hertz. Here the frequency alias back down when we go above the 500 hertz limit. So even though the input is 600 hertz, the frequency of the transmitted wave sounds more like the 400 hertz generated wave. So 500 hertz is the audio Nyquist frequency limit for this example, and any increase in frequency above this will cause the transmitted waves to be aliased to lower frequencies. And this is dramatic in the next two frequencies. Here is 800 hertz. 800 hertz aliases back down to 200 hertz. And here is 900 hertz. 900 hertz aliases back down to 100 hertz. This 900 hertz input wave has aliased down to a 100 hertz wave. That is, after it went through the gate, we got a 100 hertz wave out. This is typical aliasing for all frequencies above the 500 hertz Nyquist limit here in this example. So let's go back to 500 hertz for a moment. Here's 500 hertz. We can really understand this limit by saying that it takes at least two pulsations to create a full wave, one for a peak and one for a valley as seen in this graphic. Therefore, we have the factor of 1/2. So for this example, a 1,000 hertz pulsation of the gate only allows a 500 hertz wave to be created. This is the Nyquist frequency limit. That is, 1/2 the pulsation frequency is the maximum emitted frequency possible. 1/2 the pulsation frequency is the maximum emitted frequency possible. Okay, now that we understand Nyquist limits for audio, we need to explain the Nyquist limit for X-ray wave emission. The only thing missing is the pulsating nature of the electron. Once we've established the pulsating nature of the electron, the Nyquist limit follows automatically, being 1/2 of its rate. So, Louis de Broglie. If you recall, de Broglie hypothesized that an electron has a wavelength lambda with lambda equals h over p, h being Planck's constant and p the electron's momentum. He was correct but the interpretation was not. Instead, if we convert de Broglie's equation to kinetic energy, we have lambda equals h over p. If we use the relation the velocity equals lambda f and solve and substitute for lambda, we get the velocity over the frequency equals h over p. Now p is equal to mv. So if we substitute for p and move it to the other side, we get mv squared equals hf. Now mv squared is twice the electron's kinetic energy, so we substitute for that and we get twice the kinetic energy equals hf. And finally, if we move the 2 to the other side, we get the kinetic energy of the electron is equal to 1/2 hf, where this frequency is the pulsation frequency of the electron. I always wondered why that extra factor of 1/2 was there in de Broglie's formula, and now we know. We see that the kinetic energy of the electron is 1/2 h times the pulsation frequency of the electron. This means that when the electron hits the tungsten, its pulsation frequency is twice that of X-rays that can be emitted. This is perfect Nyquist theory, and it was right under our noses for almost a century. The pulsation of the electron causes a Nyquist frequency limit for the X-ray waves emitted, with a factor of 1/2 being the difference. Wow! That is, since the maximum X-ray wave frequency is 1/2 f sub e, then we can substitute f sub x for 1/2 f sub e and get the kinetic energy of the electron equals hf sub x, where this is the maximum X-ray frequency emitted. This is the famous energy relation for X-ray emission, and we have derived it using only the wave nature of X-rays. Wow! The kinetic energy of the electron is equal to hf sub x max. We now have a Nyquist explanation for the X-ray frequency limit. This limiting frequency is the maximum frequency actually measured in the lab, and everything agrees. All right. Isaac, do you have any questions?
Yes, Andrew. I do not understand pulsating electrons. What do you mean by this? Will you explain this better?
Okay, Isaac, will do. The new revelation we are using is that the electron's electric force is not static, but pulsating on and off intermittently, exactly as Louis de Broglie inferred. So let's bring out an electron and observe its electric field. Isaac, put up the classical electric field, please. Do you remember this electric field from what we simulated earlier? Well, we infer from de Broglie that this is not the correct picture. New wisdom reveals that the electron's electric force turns on and off intermittently like this. The electron turns on, its electric field is active, then it turns off, and its electric field is inactive. On, field active, off, field inactive. Now, this is different than the classical electric field that physicists have used for centuries. This is the new revelation. The electron's electric force field intermittently pulsates on and off. However, it is easier if you first understand the simpler classical model shown in our previous simulation, even though it's not quite correct. This will help you to understand what's really going on here with an intermittent electron. You must understand the old classical static electric field so you can grasp this new wisdom pulsating electric field. Let me emphasize this. we used to think that the electron's electric field was static. This is not possible. A static electron electric field is not possible because of self-energy considerations and because there is a Nyquist frequency limit. This new wisdom reveals that the electron's electric field is pulsating and its frequency is given by de Broglie's kinetic energy formula. Okay, so let's give this pulsating electron a kick with a voltage and watch de Broglie's formula in action. So, let's let the electron move slowly and pulsate slowly. It's moving slowly and pulsating slowly. But when we give it a voltage kick, it gains kinetic energy and it starts to pulsate rapidly. Let's try that again. Here's the electron. It moves slowly and pulsates slowly. The field turns on and off slowly. Now, let's give it a voltage kick and watch it gain kinetic energy and pulsate rapidly. To find out how rapidly, we just applied de Broglie's kinetic energy formula. We can now show a pulsating simulation that shows the Nyquist frequency limit for X-ray waves. So let's see the Nyquist frequency limit in action with our pulsating electron. Suppose the electron is going toward the tungsten anode as before, and since it has a lot of kinetic energy, it's pulsating very, very rapidly, say at 10 quintillion pulses per second. Also, let's again pretend that we're traveling right alongside the electron, and let's say it goes into the tungsten and we see it bounce back and forth inside the tungsten at 1 quintillion hertz. Then we would see 10 electron pulsations for each complete back and forth of the electron, and we would then see X-ray waves emitted that look like this. Now, I know this may be a little difficult to understand, so to clarify what's happening, we overlay the classical field on top of the pulsating one. Isaac, overlay it and use my voice to announce the different states.
Transverse wave, radial, 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 radial. Transverse wave, radial, 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 radial.
Now you can easily see why and when the wave fronts come out with each acceleration. Keep this in mind as we again turn the classical overlay off. Classical overlay off. Isaac, announce the different states.
Radial, radial. Transverse wave, radial, 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 radial. Transverse wave, radial, 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 radial.
Okay, classical overlay back on. Isaac, announce.
Radial, radial. Transverse wave, radial, 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 radial. Transverse wave, radial, 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 radial. Transverse wave, radial.
Okay, classical overlay off. Isaac, announce.
Radial, 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 radial. Transverse wave, radial, radial, radial.
Okay, notice the transverse wave fronts and notice that they are pulsed. The radial force pulsations are not part of the wave, just like the classical case. The radial force pulsations are not part of the wave, just like the classical case. They are just pulsed radial forces and are not the transverse force required for an electromagnetic wave. It's the transverse pulses generated whenever the electron is accelerated that form the wave. The electron is pulsating fast enough to emit a fairly good 1 quintillion hertz X-ray wave. No peaks are missed. Just like in our audio analogy, this pulse wave represents a 1 quintillion hertz X-ray wave fairly well. This wave will act just like a 1 quintillion hertz wave if it enters an X-ray spectrometer. All right, now let's say the electron bounces back and forth somewhat faster, say at 5 quintillion hertz. According to our formula, using the 1/2, this is the Nyquist frequency limit. So here's the 5 quintillion hertz pulsed X-ray wave. And here's the classical field overlaid on top so you can understand it better. And the classical overlay back off. Notice that with each acceleration, the electron emits a transverse radiation pulse, first a peak and then a valley the other way. We have exactly 2 pulsations for each complete wave. This X-ray wave is analogous to the audio square wave in our audio example. There's just 1 pulse for the peak and 1 pulse for the valley, or in other words, 2 pulses for each cycle. This is the Nyquist limit. If we try to bounce the electron around faster than this, the X-ray waves will alias down to lower frequencies just like the audio case. This is the origin of the limit. So, let's say that we're still traveling alongside the electron and it's still pulsating at 10 quintillion pulses per second as before, but this time the electron will get bounced back and forth at 7 quintillion hertz. Watch what happens. And here's the classical field overlay so you can understand it better. Isaac, use my voice to announce. Transverse mist, transverse wave, transverse mist, radial, transverse mist, radial, transverse mist, transverse mist, radial, transverse mist, radial, transverse mist, transverse wave, transverse mist, radial, transverse mist, radial, transverse mist, transverse mist, radial, transverse mist, radial, transverse mist, transverse wave, transverse mist, radial, transverse mist, radial, transverse mist, transverse mist, radial, transverse mist, radial, transverse mist, transverse wave, transverse mist, radial, transverse mist, radial, transverse mist, transverse mist, radial, transverse mist, radial, transverse mist, transverse wave. You can see why this new wisdom X-ray wave will alias down to a lower frequency. Many of the acceleration peaks are missed, just like the audio example. When the electron misses an acceleration, it's not on and a radiation peak is missed. Transverse wave. Transverse wave. Transverse wave. So we turn the classical overlay back on. Transverse mist, radial, transverse mist, radial, transverse mist, transverse wave, transverse mist, radial, transverse mist, radial, transverse mist, transverse mist, radial, transverse mist, radial, transverse mist, transverse wave, transverse mist, radial, transverse mist, radial, transverse mist, transverse mist, radial, transverse mist, radial, transverse mist, transverse wave, transverse mist, radial, transverse mist, radial, transverse mist, transverse mist, radial, transverse mist, radial, transverse mist, transverse wave. Notice that there are 6 missed accelerations for every made transverse wave. Keep this in mind as we turn the classical overlay off. Okay, Isaac, announce. Miss 4, miss 5, miss 6, made 7, miss 1, miss 2, miss 3, miss 4, miss 5, miss 6, made 7, miss 1, miss 2, miss 3, miss 4, miss 5, miss 6, made 7. Okay, we have a ratio of 10 quintillion pulses for every 7 quintillion back and forth. That's a 10:7 ratio. In other words, there are 1.4 pulses for each complete back and forth. We know we must have 2 pulses to generate the wave properly. We don't have enough pulses to generate a 7 quintillion hertz X-ray wave from an electron that's pulsating at 10 quintillion pulses per second. Since 6 accelerations are missed for every 1 acceleration made, the 7 quintillion hertz will be aliased back down to a 1 quintillion hertz X-ray wave. Only a 1 quintillion X-ray wave is emitted even though the electron is being jerked back and forth much faster than this. This example shows how the Nyquist frequency limit works for X-ray wave emission. The limit is 1/2 of the electron pulsation frequency, and this agrees with X-ray frequency limit experiments from the lab. We can finally understand the X-ray frequency limit in terms of X-ray waves, and this is the new wisdom. Okay, we are nearly finished with episode 1 on the X-ray frequency limit. Let's quickly review what we've learned. Number 1, the X-ray frequency limit is a Nyquist frequency limit very similar to the Nyquist limit found in audio systems. The X-ray frequency limit is a Nyquist frequency limit very similar to the Nyquist limit found in audio systems. Number 2, X-ray waves have a Nyquist frequency limit because the electric fields of the electrons are pulsating. X-ray waves have a Nyquist frequency limit because the electric fields of the electrons are pulsating. Number 3, in both the audio and X-ray wave examples, the maximum emitted frequency is just 1/2 the pulsation frequency. The maximum emitted frequency is just 1/2 the pulsation frequency. And finally, number 4, if the system tries to generate a wave with a higher frequency, the emitted wave has its frequency aliased back down to a lower frequency. If the system tries to generate a wave with a higher frequency, the emitted wave has its frequency aliased back down to a lower frequency. This concludes episode 1, the X-ray frequency limit. We now make waves with a new understanding of the X-ray frequency limit. Coming up in episode 2, we explore new wisdom for the photoelectric effect. Get ready for episode 2. This is New Wisdom Unifies Physics. Isaac, wrap us out.
We're gonna take this new wisdom. We're gonna apply it to an effect. That effect is the photoelectric effect. We're gonna see the electrons come out. We're gonna find out what it's all about. Yeah. We're gonna take this new wisdom. We're gonna apply it to an effect. That effect is the photoelectric effect. We're gonna see the electrons come out. We're gonna find out what it's all about. Yeah. We're gonna take this new wisdom. We're gonna apply it to an effect. That effect is the photoelectric effect. We're gonna see the electrons come out. We're gonna find out what it's all about. Yeah. We're gonna take this new wisdom. We're gonna apply it to an effect. That effect is the photoelectric effect. We're gonna see the electrons come out. We're gonna find out what it's all about. Yeah. We're gonna take this new wisdom. We're gonna apply it to an effect. That effect is the photoelectric effect. We're gonna see the electrons come out. We're gonna find out what it's all about. Yeah. We're gonna take this new wisdom. We're gonna apply it to an effect. That effect is the photoelectric effect. We're gonna see the electrons come out. We're gonna find out what it's all about. Yeah. We're gonna take this new wisdom. We're gonna apply it to an effect. That effect is the photoelectric effect. We're gonna see the electrons come out. We're gonna find out what it's all about. Yeah.